Welcome back, everyone, to this week's workshop, virtual edition. This time it will be LTSpice with Evan and I. So this is more of Evan's realm, but I'll try and go along, and we'll learn how to use the circuit simulation software. All right, let's keep going. So yeah, Evan just mentioned it, but the link is in the chat, so you can just copy and paste, and then you can just get started on following along with us. Excuse me. Okay, so when you first open up LTSpice, you can go along and open up a new schematic. And so that'll be just file new schematic. And then you can start placing parts so that you can begin the simulation. So I guess we'll go into that. Okay, so once you're inside the environment, first off, there's really important toolbar on the top that has a bunch of really important buttons, functionalities that you can easy access to put components into your components into your schematic, or zoom into a certain section with the zoom tools, or simulate. And so simulate is where you can run a bunch of different analyses onto your circuit that you've just designed. And so we'll go over all of the parts into creating a simple circuit, and then we'll run you through simulating it, and then how to look at the different analysis process on the circuit. So we'll be doing that, and we'll be going over 2 different circuits. So yeah. All right, so I'm sure a lot of you guys are very familiar with EE10 material, and so we'll be going over this really easy RC series circuit. And so here we showed Evan just created this. Excuse me. So yeah, it's just a very simple RC circuit, and there's a voltage source in series with a resistor and a capacitor. So if you guys don't know what a RC series circuit is, that's totally okay, but there's some really cool functionalities that we're going to explore with that, and you're just going to have to do some more research on that. But basically, we'll start with this circuit. So on the very top, that toolbar that I just pointed out, there's a bunch of components. And so you would want to select the resistor and a capacitor. And so you can just go up there, and then you can put it in. I think maybe I could.
There we go.
Perfect. All right, so I've already done this already, but let's just go ahead and clear. Is there a way? Oh. Okay, so this is the step after the make a new schematic. So you would go here and then make a new schematic, and then it'll be here. And then what you want to do is you just go up here in the toolbar on the top, and then you want to place a resistor. And so what's really cool is that you can just place a bunch of them, but we won't be doing that. And then you can use the hotkey delete to get rid of each of these. So that's a good hotkey to use. And then we want to be putting a capacitor in series, and then the escape hotkey will deselect the component. So yeah, and then after that, we want to skipping a few steps here, but we'll go over them too. You want to go into the the gate symbol here, and then that will pull up this menu where you can search up for a bunch of other components, because not all the components can fit in the toolbar. So for the voltage source, you want to just type in voltage into this little box here, and then it'll just be this source. And so you can select that, press OK, and then you can put it here.
Even for other types of simulations, say you want a sinusoidal voltage source or pulse voltage source, you'll use the same voltage, because all of those options are available when you look at the component parameters for the voltage source.
Yeah, exactly. And so I guess we'll just keep going on. I'll just explore some of the tools here. So what I've selected now is the wire tool. And so this allows you, it's kind of like the net tool in Eagle, but if you guys don't know what it is, don't worry about it. But the wire tool allows you to connect the components together. And so with your mouse, you can just hover over each of the locations. And then once you make a proper connection, it'll stop connecting the wire will stop following your cursor. And so that's how you know you've made a proper connection. And so it's kind of sticky, but yeah. And then before we get into that, we want to put in a ground. And so that's this icon here. So I've
Yes,
kind of gone through the entire procedure, but we can reiterate steps.
You can't get away with not putting a ground in because it will throw an error if you try to do it without. Like you might think, oh, okay, it's the bottom of a voltage source, that's my ground. But no, you need to put in a ground there.
Exactly. And so you can just right click to access the properties of each of these components and alter them. And so we're going to go into that. So there's a lot of different properties associated with each of these components.
Usually you'll probably just want to use the actual capacitance and resistor values since that's what you'll be concerned with. There's other parameters too, such as for the capacitor, there's voltage rating, RMS current rating, equivalent series resistance. Those are sort of parameters you might find on a data sheet. And there's actually, if you're in the select component menu, here, Henry, could you just hit the capacitor?
I'll stop. Oh.
Or actually, I can screen share.
Yeah, I think it would be better if you can.
Here.
Yeah.
Can you see my screen?
Yes.
The whole thing?
Yeah.
I'll just assume. Okay, so you can hit select capacitor, and then it'll give you a bunch of sort of pre-made ones already that you might find on, say, like a DigiKey website or something like that. So capacitance, manufacturer, type, part number, voltage, series resistance, things like that. So then you can also list all the ones that are in this database. So this is sort of also, you can change where you're looking for specific parts by changing the directory. This is sort of the standard one that you have. So it'll have all of the pre-included parts and the ones that analog devices will update with LTSpice. But you can also just create your own libraries and then have a location for them. Or say you download something and you don't really want to find where it is, you can try and find it in the directory. Yeah, so have you guys made that circuit?
Yep.
Okay, I'll just assume silence means yes.
How do you put units?
Units? Oops. So say for this resistor, you just put 10 and then you put the K symbol. It knows certain values. So like M will be milli, K will be kilo. For mega, you actually have to type out like meg or mega to make it work. Nano will be N. Femto and pico, I believe, still work. So you just use F and P respectively. Things like that.
Gotcha, thank you.
For the circuit, we're doing 10K and 220. Well, 220 micro. So then when you're also ready, we can give this a DC value. So we'll say like 3, and it already has a unit, so you don't have to include volts or anything like that. And then basically it's really super simple to actually simulate it. You just have the running man up here when you're ready. So for this, on the first time, it'll bring up the edit simulation command. So we can pick sort of what type of simulation we want to do. It's transient, AC, DC sweeps, and then a few others that you can do. Not necessarily useful in this circumstance, but we'll say for this one, we want to stop time, say 1 second. We can always adjust what we view. So maybe including too much time is probably a good thing, right? So stop time, we're not really concerned about the maximum time step. It'll just do normal one that it will calculate itself. So we're running for that. So you'll have this simulation menu. This is basically where it'll plot the data, but there's nothing plotted right now, right? So to get the plotted data, we actually have to go back to the circuit and then select the thing we want to see. So when we hit the, click these net components, we actually get voltages, while if we tap the actual components, we'll get the currents across them. So say this is voltage here, current across a capacitor, and current across a resistor in this time scale, right? So if we increase the time scale, we would be able to see that, okay, this would go to, well, it already is sort of constant just because you can see there's very, very minimal change in this value from the circuit. Yeah. Does anyone have any questions on like just sort of this normal DC analysis of circuits? Or like say, what sort of time scale you want to look at for a transient analysis? Okay.
I have a question. Do the colors mean anything on the simulation panel? Or is it something that you can assign?
It gets assigned in an order. So right now I have this one as being blue, so that's this. If I select another one, it will end up being green. If I select another one, red, and etc.
So each component will have their own color code for their voltage and current?
Sort of.
Okay.
So you can reset colors and things like that.
I see, yeah.
Another sort of useful hint is just if you don't want to see as many things, you can obviously try and delete the traces. But the easiest way, if you just want to view one component, is to double click on the trace that you only want to see. So if I only want to see this one voltage, I only see the one voltage again. But having multiple things to actually compare is good sometimes too. What's the next portion?
Yeah, I could go back to the slide.
Oh yeah, we were just gonna do a pulsed source example now.
This is whack. Yeah, so we've gone through a lot of these steps already, but just to make sure we didn't miss any details, we've put them here. All right, so let's see. So yeah, we've so we put on the components, and then we put on the specific units, and then so that gate like object in the toolbar allows for you to access a lot of different library components. So you can just go online and just download a bunch of LTSpice compatible components, and you can have them modeled into your circuit. So that's really useful. So for the voltage source, we did a DC one, but obviously for voltage sources, you can have a wide range from DC all the way to all the AC ones, and you can have transient responses. And so you can feature all of that into your one source symbol that you have there. So it has that advanced capability. And so we'll be also going into a pulse style voltage and a AC one later in this workshop.
So yeah, here. How about you guys just try out, or can you go back to the pulse one? Oh wait, no, it's 2 slides ahead, I think.
Okay, so we can, yeah, so like you said before, the ground and wires have to be on the circuit, and you have to actually connect each of the components to ground so that you can have a running successful simulation. So yeah, here is the pulse source that Evan was going to talk about for the voltage source.
So yeah, go back into your actual simulation. Just right click on the source. Well, you'll want to actually exit out of the graph on top, and then just make the bottom circuit full screen. So then we'll right click on the voltage source, and we'll go into advanced to bring up the other options menu. So for this one, yeah, we'll go to pulse. And if you're using the same R and C values we were using, we're going to want to plug in, oops, there we go. 0 volts for the V initial. So that means we'll start on basically 0 volts. V on will be 3, T delay will be 0, T rise will be basically just very, very small. So like 0.000001. Same thing with
5 zeros.
T fall because we're making a square wave. T on will be 10 seconds, T period will be 20, and then you can leave end cycles blank because if you don't put anything in that actual parameter, then it will keep on cycling this. But if you want to say a specified number of them, you can put in a number. I think in the slides it has 10, but don't worry about that. So these actual parameters, T rise and T fall are basically the rise and fall time of the on and off cycles. So basically when it goes from 0 to your V on voltage, it's how long it takes to get there. So depending on what type of wave you want, you might want to change that. If you end up putting 0 in there, it doesn't actually make it 0. It will default to sort of a linear transition between your V initial and 3, or your V initial and your V on. And I'm not exactly sure what it decides as the slope, but it's more triangular than a square wave.
All right, so we want to go ahead and simulate this.
Mm-hmm.
And so did you want 20 seconds for this? Okay. Oh, I have 2.
Actually, you probably want to make it like 100 seconds. That way you can see more of the actual change,
Okay.
well, more cycles.
I'll go back and rerun. Oh. Maybe this is something you have to
Did you run it?
edit simulation command. Okay, so
Yeah.
100 seconds.
Mm-hmm. So to change the simulation setting again, like the first time it will bring up the simulation menu for you.
Okay.
The second time you have to go to simulate and then edit simulation command.
Got it. So simulate, edit simulation commands will bring up back, and then you run the simulation again.
Mm-hmm. So it's run. So Henry, can you select some of the nodes now? Or the nets? So put your cursor on the actual like line connecting components and not on the component, because right now you're getting currents. There we go. Here, wait, double click it and you'll only see that one.
Got it.
So you can see how we're actually outputting a square wave now.
Okay, and then here after the resistor, there's a voltage drop. So it's not going back. Oh no, it's just the. Okay, so yeah, DC analysis of an RC circuit isn't really something that's useful information, but we can go into more of or pulse analysis, I guess. But we can more go into the AC side when we simulate that with our AC voltage source. So I guess that's going back to the slide. So yeah, basically you can just analyze the different realistic or simulated values of your circuit. And so you can use this to check your 110 homework, and you can basically make your circuit and then go in and see all the different currents and voltages at different points of the circuit.
Henry, can you
Yeah.
click right before the capacitor? Yeah, I think there's something up with your simulation because that's actually not what I'm getting.
Okay, do you want to go ahead and share your screen then?
Yeah, because this is
Okay.
supposed to be showing you like basically the RC charging time.
Yeah.
Here,
Okay.
let me share my screen. There we go.
Oh wow, that's nice.
So this is our normal sort of square wave that we're doing, right? But when we actually look at it, we can see the RC charge time from this circuit. So you can see that the full charge time is around 10 seconds while the discharge is 10 seconds as well. So this is sort of why we chose this. But yeah, you can also see the current across the circuit as well as the current across the resistor. I mean, they'll be the same, but sort of makes a cool plot when you plot everything together. But this is just a normal RC example. So this might be something that you would do in, say, EE10, and then here we can add some more components to this. So say we add another resistor and maybe like an inductor. So we'll make this a series or a parallel RLC circuit. Okay, so we'll give this a value. Let's say 100 microhenries. Oops. And this will be 10K as well. So we can see how it will look when we rerun it. So here's our square wave still. We zoom in, take the voltage across the inductor, voltage across the capacitor. So we can sort of see like the properties that we would expect to see when we have a sudden change in voltage for, say, the inductor. We just get these normal like sort of impulses, right? But if we look at the current, we see the square wave again in this versus having these weird sort of spiny shapes. Okay, here we'll go to another. Technology
going
today
back.
is.
Yeah.
There we go.
I'm trying to remake the circuit right now.
Wait, Henry, I had my ground hooked up. It kind of how it was on your screen at first, and I was getting the same output. But then I changed it so it looked more like Evan's, where the wire didn't connect to the bottom of ground; it connected to the actual.
Okay,
wire.
so there's like a node on top. Okay. Yeah, so that is pretty tricky. I'll try.
You can see if you connect to ground more down here and then have a node connecting up to here, that'll work a bit better. I'm not sure why there would be a connection on the bottom. I actually haven't done anything like that before. So, okay, here we can also try this with an AC source. So this will, oops, sorry, produce even better results. So here, I'll go back into this. Undo. Yeah, there's no like easy Control Z for this. You just have these two buttons at the top. Their actual shortcuts are like F11 and F12 or something like that. But yeah. So also when you want to do a different type of simulation as well, you have to take out the simulation component that's on the bottom. So we'll change this into a sinusoidal example. Can have the, don't worry about T delay because that just offsets the when you start the wave. Theta is a decay factor for the sinusoidal wave. So if you want a decaying sinusoid, you could put in a theta factor, and depending on the frequency that you choose for it, it will change. So we'll say like, we'll put in 10K, I think, as the frequency. And then we can sort of see how this will act as a filter, right? Since usually when you do an RC series circuit, that's a low pass filter. So here, I'll change that. We don't need to change the transient analysis because we still want to see how it will act in time, but we might want to change the time scale. So since this is rather high frequency, maybe we want to do like 0.01 seconds. Oops. We don't want just 20 seconds. So here's our sinusoidal signal. Well, our actual signal. So 3 volts amplitude, or 3 volts amplitude. So 6 peak to peak. Take a look at the current. Then we can also see. Well, this isn't the best way of looking at it, but you can sort of see how the voltage goes down. Here, actually. Trying to remember what setting I had. Right. Okay, so did you guys get that? I will assume
What
yes.
did you click?
Yep.
For which component, like to change what?
To get that thing.
The weird squiggle line?
Yeah, you click between the resistor and the capacitor, right?
Yeah, so this is the voltage across the capacitor because it'll take this voltage at basically this node and compare it to your ground voltage. So this is actually still technically like rather similar to the voltage on here. So you can see like, okay, this is 0.6 volts versus this is 3 volts, but it's, rather DC. We can actually change that by increasing the frequency. So if we say go to 10 megahertz, so we have to include the mega, we'll rerun it. Well, we should also change the time scale. So it'll take a really long time to do this full wave if you let it go on. So this is 0.00001. You can also pause the simulation or halt it and rerun. Oh. There. Now rerun it. That's much better. Actually, we can even change this time scale even more. So you see how there's a ruler on the sides of the screen? Basically, when we right click, we can change the bounds and the tick marks that we're doing. So if I want to decrease the amount of time I'm seeing, I can change this just to 1 microsecond. I'll change the ticks to 0.1 and we'll see much less waves. It's really easy to do that. On the right side also, we can change the top and bottom voltage if you want to change the extents, or you can even change the logarithmic if you want, but not necessarily useful for this application. There might be certain circuits where it is. But when you change back, it'll go back to some normal random values. So you'll have to remember what it is, or else you can go up to these settings. So there's auto range and things like that. Also pick visible traces. This basically shows you all of the component or all of the parts that you could actually be labeling on here. That's right. So if I include IC1, that's basically just the current that's going through the resistor. Sorry, IC1? Never mind. That's going through the capacitor. If you want to make it easier for actually knowing what's being labeled, oops, you can include net names. Oops. Oops. These are ways just to label net, and then you can give it a name. So say this is VN. Put a name there. Rerun the simulation. See how it's named VN now?
And that was a right click on the trace.
Yeah, you can, right clicking basically gives you all the options that you would want for certain components. So like, say for this one, it's ground, right? So 0, things like that. Let's try to do a different type of simulation. So we'll go back to edit simulation command, and we'll try and do an AC analysis now. So basically it will sweep through different frequencies, and that's what it'll be plotting against. So we'll do decades, number of points per decade, say 10. Start frequency, we'll have it at 1 hertz. Stop frequency, we'll have it at 10 kilo. And we'll see how it does. Oh, right. It's because I have multiple requests going on. So delete that. Basically, to delete the actual thing, you just go into the text editor, or you'll double click it and you can delete it. Now it's gone. So we'll go back to edit simulation command, AC analysis, decade, 10. We'll go from 1 to, we can actually make it a bit higher. So we'll do 100 mega just to see that there's a bit more change in this circuit. Place it, simulate. Oh, right. You actually have to change the source a little bit too. When you want to do an AC analysis, you have to go and put an AC amplitude in it. Usually we'll just select 1 for this.
And for those of you who don't know what a decade is, it's a change in frequency by 10. So 1 decade would be from 100 hertz to 1000 hertz.
Right, so 1 hertz to 100 megahertz up here. So we're just looking at VN, but say this is on a dB scale. If we don't want to look at it on a dB scale, we want to see like actual voltage, we'll just go to linear. Okay, and we can see how current is affected by frequency, or even something like voltage. So we can already sort of see how this one would be a low pass filter. At low frequencies, it'll actually allow voltage to pass, while at higher frequencies, we don't get voltage off of this node. And then usually for these types of graphs, there'll be two lines associated with these AC analysis most of the time. One of them will be magnitude and one of them will be the phase, right? Okay. So you guys sort of get how we do AC analysis? Basically is we'll change the simulation command in the edit menu. We'll do AC analysis and pick the type, the number of points per decade, and then our start and stop frequencies. And then we'll change our source. We don't actually have to do a sinusoidal source for this either. We can actually do a sort of non-DC type, and it'll still have the small signal AC amplitude so that we can use it in the AC analysis. So when we simulate, it'll be the exact same thing, but we can also go back in and change some of these values and see how they affect the circuit. So if we're using a 10 ohm resistor instead of a 10K, you can see how the circuit will change. So at high frequencies, the resistor is the pass component because this is the current across it. So if you want the voltage, you can just do I times R. Here. Also, we have one more example that's a bit harder. So I'll actually show you the circuit I want you to make.
It's the op-amp one.
Oh, there's also a way of sweeping sources. It's more of just another DC analysis where you'll change the input. So this might be useful if you're, say, you want to increase the voltage you apply to a circuit. So say you want to get the transfer characteristics based on you changing like a voltage input or something like that, or a current input. So yeah, this will be the circuit that I want you guys to make. Here, I'll actually present this. Can you guys see that?
Yes.
So you just have to get 3 resistors out, 3 sources, the op amp. So you can just type in, it'll be in a specific section. So if I go
How do you drop rotated resistors?
How do you drop rotated resistors?
Like how do you rotate a resistor before dropping it?
I believe it's just Control R.
Control R. Okay, thank you.
Yeah, it's just Control R. Woo. Okay. Here, I'll put the circuit back up, sorry. And then you can also label the nets if you want, just by, for this one, you don't have to, but you can just do the right click and then net label to label the input and the output. You can also give the resistor specific names as well. But yeah. You can also see that there's a positive and minus V connected to the op amp. Just basically by labeling these nodes, we can connect them to this voltage source. So that's sort of how the op amp requires these voltage rails to operate. So that's why we have these secondary supplies.
Okay, for me, I didn't have that specific op amp, but anyone should be okay.
Wait, do you
right?
not?
I have OP07.
Here. I can show you where it is. So basically, we'll go in, op amps. OP1177. Yeah. But if you use another op amp, it should be roughly equivalent because this is just sort of a normal, basically, what was this called? Oh, not an inverter. Oh.
Voltage follower?
Yes.
I'm still having a hard time turning my resistors.
Control R doesn't work?
Control R while you're hovering over it, right?
Yeah, so here, I'll go back to my screen. Whoops. I'll take a resistor. So I have it where I'm able to move around. For me, it's Control R. I'm not sure if there's another shortcut for it though. Otherwise, when you place it, I believe there's an option to rotate components. So
you have to actually like pick it up first, then.
Yes. So if you want to pick something up, you can hit the move or the grab.
Oh, okay.
So move, Control R. Otherwise, I think, yeah, there's not actually an option, I believe, to, oh, right, rotate, Control R, mirror, Control E. So if you want to mirror it about an axis or something like that. Yeah, sorry, I keep moving away from the circuit.
If you want to do it through the file or the edit command, you can just go, after you've selected the component, I think, edit, and then there's a rotate command there.
Here, I'll do it along with you guys. I think I can do this pretty fast by now. What is this one called? Oops.
Voltage follower?
No, what's the name of the op amp?
OP1177.
OP117, okay. I hope no one's looking at what's going on. Haha, I beat all you guys.
Oh.
Yeah, so LTSpice has a bunch of pre-made circuits basically, if you want to use them. So you can go to open, and it'll basically just open up the LTSpice folder. So there's the examples library. These are ones that I've done in the past, but you can go to examples, educational or jigs. Jigs are more small circuits, while educational ones are the ones that the people from Analog Devices have usually made. So say we go into educational. So Butter, I'm assuming, is probably a Butterworth filter, band gaps, probably a filter, audio amplifier, things like that. Curve trace. Varactor circuits, universal op amp. Here's just an example of some of the stuff you can make with it. Oops. Oh, this one is not that impressive. Yeah, well, that is also not it. Yes, this is a bit bigger of one, but so yeah. So once you actually have the circuit, basically you can go in between the things that you're doing with the top menu. So this was the draft I have of the first one. This is the first circuit. If I don't want to look at this anymore, I can just close it. Say for this circuit, it's got a transient analysis for it. So when we're ready, we can simulate it. And now we'll select points that we want to look at. So this is the output of the circuit, while this is the input. So basically, since we're doing a sort of a linear look at it, V out is twice the input. So that means we have a gain of 2 on this one, I guess. You can also go around and say, play with the components. So if I change this to 100K, we can see what it'll do to the gain. Whenever you make a change though, you have to rerun the simulation. So this is greatly increased the gain. Oops, that's not it. That's also not it. So say from 0.5 volts on the input, well, it's still a 1 volt sign, but yeah, so there's LTSpice in general is like pretty powerful for circuit analysis. The main drawbacks though is that if you actually want to create your own components to use in it, it's rather difficult because you have to write SPICE directives for it, for how the component operates based on certain stimulus to the ports, right? So that's a bit beyond the scope of what I actually know in terms of LTSpice, but for general circuit simulation, so for your first order, second order RC circuits, or normal, like just sort of amplifiers that you might want to try in a circuit, they're very good. But yeah, I would highly suggest using this if you're doing your homework for EE10 or 110 or something like that. If you're not exactly sure how an output will look, this will basically show you exactly how it will look. Because you can put in, say you have, one of those really wonky circuits where you need to put in multiple voltage sources and current sources at the same time. It will apply the rules that you need for that circuit, so the KCL and the KVL, and be able to tell you what it is so that you can verify results.
There's also the .param tool that you want to explore. There's .op on the top.
Oh, right. Did I get taken out? I thought I had a slide for it. Well, anyways.
Oh, it's at the very end. The second to last, but yeah.
If you, this is basically the SPICE directive button, this .op. A useful one that you can do is .param. Basically, we'll hit OK, and we'll place it down. But when we go actually into it, it gives us this param statement thing. So now we can add, say, this is a way of adding variables into the simulation. So say I wanted to make V in, and we'll give it a value. So V in equals 10. Well, I mean, we use 3 throughout this whole thing. So if I want to go into this, I can do, oops. Oh, whoops, sorry. Can't actually use it in those parameters. Can't remember where I was using it from before.
That's okay. Maybe we can just update the slides with the exact steps. So we're going to put the exact steps so that you can create your own SPICE directives. And that's just a way to add more functionality to your circuit. So it's basically making it easier for you to use. Yeah, you can do a whole lot of analysis with pretty much all types of circuits, and the libraries on LTSpice are pretty big, as you can see with the by searching up the components, you can find like all sorts of different models and stuff. So that's pretty cool. But yeah, I just recently learned about LTSpice, and I'm in 110 now, so I'm definitely going to use it.
This isn't the only SPICE simulator out there. Like literally there's probably dozens of them, just because most companies sort of have their own proprietary one that they use in-house. So it's good to know how to use them, but they will vary. So another one that I've been using actually is EDS, which is a bit more advanced, but it's for a class. It lets me do high frequency, basically design checks, and be able to modify MOSFETs and things like that to sort of parameters that I need to be able to check on them.
Evan, what does SPICE mean?
SPICE?
Simulation program with integrated circuit emphasis.
Yes.
Thanks.
Simulator program with integrated
cool.
circuit emphasis. So basically, most of the companies that end up making their own ICs or that like have that do any circuit work will have some SPICE program that they end up putting their circuits into to first test them out before they actually, use discrete components to make them, because they want to see, they want to be able to test how the circuit will react just in a sort of test environment where they don't have to build anything yet. And for the most part, these are very, very accurate results. But a lot of programming does go into how each of these works. So yeah. Here's an ADS example. Whoops. Uh, 163 dB. So this is like another SPICE simulator where you have your MOSFET and your sources as well as current probes and do simulations. Then end up making plots from them. Oops. But yeah.
Nice. Thanks, Evan. That's pretty cool. That was for your microwave circuits class?
Yes. The only way that you're going to be able to use that particular software, though, is if you're actually taking a microwave class, or if you take 162, which is an antennas class, just because it's very, very expensive per license. So the school doesn't buy them.
Oh.
You have to get like a license trial through the teacher.
Oh, shoot. Okay.
But
that's pretty cool.
I definitely prefer that software over LTSpice because it has so many more functions on it.
I guess LTSpice would be a good place to start then.
Mm-hmm.
Yeah.
It's also something good to write on your resume. Like I'm sure many of you have looked at job applications, and one of their preferred skills is to have some SPICE simulation experience. So LTSpice is a good place to start if you don't really know much about it, or if you don't want to try and use more advanced software. The other company that does a lot of simulation, I believe, it's Cadence. They have several, I believe, but I think the normal one is like Allegro. But yeah, those might be the ones that you would be working on in an internship sort of setting or in a normal job environment. Just because LTSpice is freeware, so you're probably not going to use it other than personal projects or for like sanity checks.
But the environment's like pretty similar in terms of how to simulate and everything. Nice. Yeah, so I guess that concludes our workshop for LTSpice. It's a basic introductory one, but we'll post the slides with more information so that you guys can use like LTSpice on your own. And it doesn't take that much space on your computer, so it's really nice. But yeah, thank you guys so much for coming out. We also have another announcement for people who are interested in becoming workshop managers. I think I spoke to several, but basically we're going to be coming out with a email detailing like the interview process and basically listing out all the requirements that we expect at the interview. So that will contain like all the specific details, and then hopefully you guys will be really prepared and it'll be really fun. So yeah, workshops this year is really competitive. So it'll be a very tough choice to pick out the next year's workshop candidates. So that means workshops next year will be very good. And I also heard that IEEE, out of all the IEEE projects, workshops has the most.
Oh no, that's not
Is
true
that
anymore.
true? No. Oh, heartbroken. Rest in peace. Second most?
Is Evan, which one is the most? You seem to know.
Alex, am I at liberty to say now?
No, I think it should be obvious if you're applying for that specific project.
Oh yeah, it should be pretty obvious.
Yeah.
It is what you think it is.
I think
all I can say.
I think I know what it is, but I just was trying to get some insight. Okay. Thank you guys for the workshop. I think this is one of those things where I'll need to just practice to get more used to the environment, but it does seem really useful. So
yeah, definitely. It's kind of like Eagle, but all really cool stuff. And I just overheard in like my 110 lecture, the professor was talking about LTSpice, and he was like, people don't touch this until grad school. So if you just kind of
Okay.
explore with it and play around with it.
You might not
Okay.
again touch LTSpice per se. There's lots of other ones. So like I'm in 115C right now, and we have to use another circuit simulator, but this one's more for MOSFETs, and it's Cadence Virtuoso.
Thank you guys so much for coming out. Make sure to check out our other videos for our other workshops on the YouTube channel. And yeah, thank you guys so much.
Like and subscribe.
Yeah, like and subscribe.
All right. And
All right.
don't forget to hit the bell to join our notification squad.